Welcome to EDU World Space.
So when we want to calculate something like the gravitational acceleration on a different planet, we do have to revisit Newton's law of gravitation. So once again, that's going to be the force of gravity is going to be equal to the gravitational constant, the mass of one object, the mass of another object, all over the distance between the two objects squared, right? But we're not just looking for the force of gravity, right? We're looking for gravitational acceleration. So if we really wanted to rename this FG term here, this FG term would really become the force of gravity is equal to the mass of an object times the gravitational acceleration, right? So specifically speaking, let's go towards the moon, right? So the force of gravity on the moon would be equal to the mass of an object on any object on the moon times the gravity on the moon. So we can connect these two together because we have Fg and Fg, right? So if we're talking force of gravity on the moon, it would equal the mass of an object times the gravitational acceleration on the moon. And that would also equal the gravitational constant, not concept, the gravitational constant times the mass of the moon, and moon times the mass of an object, once again, arbitrary object. And we would start talking about not just the distance between the two objects, but the radius of the moon itself. So we're going to name that Rm. And that's, of course, going to be squared. So if we wanted to reconcile these two equations, we would be able to divide out this m, right? This m now goes away because when we divide it out, we'd put the m here and it would cancel, right? So that being said, we're going to end up with an equation that looks a little bit like the gravitational acceleration on the moon will equal our gravitational constant times the mass of the moon and moon over the radius of the moon. So Rn squared. So when we plug those values in, those values are specifically going to be for G. That's going to be 6.67 times 10 to the negative 11th, and that's going to be newtons per meter squared, kilogram squared. All right. And then the mass of the moon can be sourced as 7.35 times 10 to the 22nd, right? Big number, big number. The radius of the moon is also going to be 1.74 times 10 to the 6th. This is going to be in meters. And our mass of the moon is going to be in kilograms, right? So we can go ahead and plug this in. So this is going to be 6.67 times 10 to the negative 11th. This is going to be multiplied with the mass of our moon, which is 7.35 times 10 to the 22nd, right? This is going to be over, once again, our radius. Oops. You already know this, the radius. It's going to be 1.74 times 10 to the 6th squared. So when you go ahead and do the math out, you're going to get an answer that looks a lot like what our actual answer is. So our answer here is going to be 1.619 meters per second squared, or approximately 1.62 meters per second squared. So this acceleration due to gravity on the moon will come in handy when we're talking about things like reaction forces, right? So if we're going to go ahead and work with this, so if we're going to say we have an astronaut with a backpack, and she's walking around on the moon with her backpack. And we want to know the reaction force at her hip joint, which in general is a very good thing to know because we know it's not going to behave the same way on the moon as it does on Earth. So that's going to mean a lot biologically speaking. So if we have our astronaut and she is on the moon, she's got a backpack. So our astronaut has a mass. So a massive astronaut has a mass of 65 kilograms. And her backpack massive backpack is going to be 43 kilograms. Sorry, that's her backpack. Shade in the backpack. All right. Mass of the backpack, 43 kilograms. Now, we know that the reaction force, right, her weight is going to be the cause of this reaction force, right, her total weight. So it's going to be mass total times the gravitational acceleration of the moon, right? So we know we have to add these two masses together, right, to get our total mass. So MT is going to be 108 kilograms. Now, that being said, we have 108 kilograms. We're going to multiply that with the gravitational acceleration of the moon. So our weight, her weight on the moon, is going to be 108 times 1.62. This is going to give us newtons, right? Because 108 kilograms meters per second squared, that's going to equal Newton. And when you do this calculation out on your calculator, you're going to get a weight of 174.85 newtons, right? Now, we need to also remember that we are in a directional situation, right? We have x positive and y going upwards, which means gravity is actually negative, right? So because gravity is negative, I'm going to do it in red just for emphasis, we're going to need to make sure we have a negative sign here and a negative sign on our answer for our weight, right? So this is going to be negative. This is important because our reaction force, the force pushing back up on our astronaut, right, our normal force, is going to be positive, right? Every action yields an equal and opposite reaction. So our normal force is going to be a positive 174.85 Newton force. This is important because if we want to know the force of friction at the hip joint, so hip joint, mu, our coefficient, let's say it's 0.005, mu is going to have to multiply with our normal force, right? So our force of friction is going to equal mu, our coefficient, so mu kinetic, times our normal force. So that's going to be times NF. Now, if we plug this in, that means we're going to get 0.005 times our normal force, which is 174.85. And when we do that out, we're going to get a friction force of approximately 0.874 newtons. There we go, 874 newtons. So this is our reaction force right here for the moon, right? So if we were on Earth, so let's just, if we were on Earth, this would change, right? Because now we're saying, okay, our weight is going to be mge, negative mge, right? This is our weight. So it's now going to be 108 kilograms times 9.81 meters per second squared, because that is the Earth's gravitational constant, or Earth's acceleration due to gravity, excuse me. So that's our g for Earth. So this will yield us, once you do that calculation out, that's going to be approximately, once again, it's going to be negative because gravity is negative, It's going to be negative 1059 newtons. Same kind of concept. The coefficient of friction in the hip joint isn't going to change just because you're on Earth versus if you're in space. So UF times NF will equal our friction force, right? So we have 0.005 times a positive 1059. Once again, this is our normal force. And that will yield you 5.29 newtons.